Welcome back to part 4 of our 5-part series on using Apache Spark and Redis. We've taken a look at a lot so far, including even just getting familiarized with Docker and Apache Zeppelin and Apache Spark for those who hadn't actually seen them before. Then we took a look at kind of a typical process for just getting started very slowly with using Apache Spark. So we imported data, we took a look at the data, understood the properties of that data. We then added columns to mutate the data, took a look at using the SQL interpreter to kind of quickly analyze our data and kind of get those chops up. Then we exported our data to Redis and took a look at using both binary model and kind of typical model for our export to Redis, which is basically just saying how is it that we're storing our data? Are we storing it either as like a binary key, or are we storing it as individual fields within a hash map? Then we took a look at, in part 2, how do we re-import that data? So how do we read the data back from Redis into Spark so that we can actually start to really explore that data, understand the characteristics of the underlying data, what patterns do we see, and then also, really what can we do with the data? Are there any kind of questions that are kind of bubbling up from that data? This is a typical process for most machine learning projects where you were starting off with a brand new data set. You don't know potentially, where does it max out? When do you need to add new data to that data set using ETL flows, which is extract, transform, load. In this case, we're reading our data and we're saying, okay, well, there's new characteristics of the data that we want to explore. Let's first run some tests and explore that through the exploratory data analysis phase. And then let's see if there's more that we can actually do. So how do we kind of iteratively drill into the data to really understand more about those characteristics? So that was basically part 2. So part 3, we started taking a look at, well, now that we understand more about what the data looks like and those characteristics of the data, how do we actually prepare something for machine learning? So humans understand, strings, they understand, kind of stories and visuals a lot more than a computer, which can't really see. And that's just computer vision as well, but in this case, let's just consider a computer as kind of it's a thinking machine that doesn't necessarily understand humans. We try and feed it data in a specific way that it understands so that it can then help to predict specific outcomes and or help us to further enhance our own understanding of these things. We took a look at unsupervised learning. We took a look particularly at k-means clustering, which is a method of taking unsupervised and or unlabeled data and reading through a feature set and being able to then cluster that data into logical subpartitions. So we used we used the data set from Netflix. We took a look at how ratings and categories affect the ability for the machine to be able to really add a label, or in this case, add a cluster point that says, how do, thrillers and R-rated movies, horror movies and R-rated movies, like how is all that stuff actually clustering? We sort of maxed out what we could do with clustering. So we took a look at also how do you layer in domain knowledge. So as a human thinker, teaching a computer to think, we know more, at least we hope that we know more than the actual computer. Sometimes we have to actually give it a little push to be able to have it think kind of more logically like a human. So this is actually something that's really important for a lot of machine learning problems in general. If you can actually dictate explicitly how you want a computer to think, typically this goes through like a human labeling process where you're taking data and you're saying, this was a problem, this was not a problem, or this is a characteristic of X, Y, or Z. That process is super useful when you're actually getting to the point of maybe taking a model to production, whether it's for fraud or anything else. In this case, we're making a classifier for kid-safe content and non-kid-safe content. So basically teaching the machine learning model how to understand ratings and categories in the Netflix data set. So that's basically the recap. We also took a look at a lot of different things like pipeline functions. How do we ensure reliability when feeding a second iteration of new data into our model? Like how do we ensure that we're repeating the same exact steps? We're going to actually go a little bit further into there, and we're taking a look now at creating custom transformers, serializing and or saving off our pipelines. And then we're taking a look at linear and logistic regression. So logistic regression actually first, because it's a little bit easier, because it's only classifying a true or false. So what is the confidence score that something is a specific class. In this case, the specific class is kid-safe or not kid-safe. And so we're going to take a look at that now. So if you already have everything else fired up from the first session, or the second session, or the third session, everything should just basically work at this point. You're going to still have to bind the interpreter like we've done across the board from the past notebooks. That's okay. Just bind Spark and Markdown. Other than that, you can basically detach all the other interpreters, save, and then you'll be ready to go. So I've already done that, and let's take a look. All right, so we've now loaded the notebook for part 4, and we are going to now take a look at kind of extending what we did in notebook 3. So we took a look at transforming our data using our rating index and then the rating class. And all we're going to do here is now kind of formalize that. So I briefly talked about in the prior notebooks about transformers and estimators. So anytime you see transform and fit, you're taking a look at a process that has been identified that requires extension of this transformer interface, and then also extension of the estimator interface as well. In Scala, we call them traits. All it's doing is basically providing like an abstract framework for us to be able to reliably create these pipeline stages, which are the individual mutations along a series of transformations or a pipeline. So data comes in, as we know, we've read it from Redis, and that data then gets transformed over a series of deterministic steps. So we're always expecting the same exact output from the same exact given input for a version of this pipeline. So with that said, let's take a look. So we have this rating classification transformer. So what the rating classification transformer is doing is it's using the transformer interface, and it's also bringing in the with means I am extending one module and I'm also bringing in another module. So it's called a mixin in Scala. So here we have a transformer, which gives us our transform method. And then the default params writer, we're not actually overriding anything from the default params writer, because all it does is say, if there's nothing that I'm actually sending to a constructor, then all I'm going to do is basically serialize this process as is. So I'm just going to use like a object serialization. So with that said, let's go into this a little bit more. So we have our safe for kids and we have our safe for most. We saw this before. We also have this, the transform schema. So we talked about schemas before and the struct types. And we looked at like the DDLs to be able to take a series of strings, like a create syntax for a SQL table, that created an underlying schema. The schema backs our data frame, and we know that we're working with data frames and data sets. In this case, it explicitly, basically, the end result is a data frame, which is a untyped row in Spark. That doesn't really matter. All we really want to say about this is that it's more of a strict process. So instead of saying, okay, well, we have this like loosey-goosey series of functional transformations, someone might go back in the code and change it later. All we're doing here is saying, well, we're going to now formalize exactly what we want so that we can store it and save it and serialize it for later. So we're going to look at that as well as we kind of go on. But back to the transformer. So transform schema. We have a specific schema that we're expecting. So at least we expect that rating index, which is a double. So taking a look over here, we expect that rating index exists in the data frame and it's a double type. If it's not, throw an exception because we can't do anything else in the pipeline at this phase of execution. Otherwise, we are going to now mutate the schema of the data frame. And this is kind of a promise that says, as this pipeline transformation is occurring, this is a phase of execution that is giving us this specific rating class field. That's all it's really doing. It's basically telling Spark what it wants to be doing. And then when you call transform now no longer has to do any validation because it's being done before. And then at that point, I can say, okay, well, given that we have a rating, we want a rating class. We're using our with column. So with column rating class. And then nothing else changes here. We're doing our when condition, our when conditional from before. So when the rating index is in the collection safe for kids, it's a 0. When it's in the collection for for safe for most, it's a 1. Otherwise, it's a 2. The nice thing here too is that if we start adding more categories, so say Netflix adds a bunch of new categories, you haven't seen them before, we don't have to necessarily update this version of our pipeline to be able to support that. We're just saying that, well, as a blanket statement, we don't know yet, so we're going to throw this into the bucket of not safe for kids. And then we could go back, we could retrain this, we could update this, change the version of it. So In the case where there's a mutation or a change to the version, all we do is basically bump this, the UID. So in this case, given that for this training, we're never going to change this, we just have this as a static UID. So the UID is basically used to basically denote to the JVM that this class hasn't changed since the last time it was serialized. So it's safe to keep on safe to keep on using this. I won't go into any more detail. So that's pretty much it for the rating classification transformer. It is denoting what's safe for kids, what's safe for most, or what's basically a grab bag of stuff that could, it could be adult content. We also maybe don't know about it, could be unrated, etc. So we just know that it's not safe for kids, and we're assuming it's not. So rating index comes in, rating class comes out. Is kid safe transformer is now taking, literally, if we have a 0, it's kid safe, otherwise it's not. So same exact thing as before, we're extending transformer. We're bringing in the default, the params writable. This is allowing us to serialize this. So same thing as before. We're saying we're not going to change this, so it's kid safe transformer as the identifier for this class if it's serialized. Transform schema is expecting that there's a rating class, and the output's going to be a label. So then again, transform. Again, this is how we transform it. So our data set comes in, data frame comes out. So this data frame with column label. So when the column rating class is equal to 0, it's a 1. Otherwise, it's a 0. And so this is basically our way of dictating whether or not it's a, it's a true positive. So is this actually, when the machine learning model is reading through this data, is it kid safe or not? And that's pretty much all this does, but it does it in a reliable fashion. From there, we're creating our params reader. So an object in Scala is basically like a static class anywhere else. There's only ever going to be one instance of this object. So the rating classification transformer is basically our only entrance to being able to read what we actually wrote if we were to serialize the class above. And this is actually kind of a nice thing because you don't have to worry about creating a bunch of different interfaces or a bunch of different classes, having some kind of pool where you're ensuring that there's only one version of the class. Scala has basically wrapped that up. I know Kotlin has the same kind of primitives as well for these kind of objects. But regardless of that, this is how our reading is done once we've serialized this stage of execution in a pipeline. We're going to take a look at that in just a sec. So those are out of the way. And then we're going to go through exactly what we did before, only now we're actually using our hardcore stages to be able to do a full transformation. So going back to structure and going back to the DDL. So we have the Netflix category data with rating. So we created this before. So a show ID, a category, and a rating. Pretty simple. That has a structure. So we're using our struct type from DDL for a Netflix category with rating and schema. From there, we're now basically reading our data back out of Redis. So we're saying Spark read Redis using our schema, which is this schema we just created above. Our key column is our show ID. And now we're going to be reading from our Netflix category rating table. And then once we call load, it's a lazy promise that we are going to be loading. So I will open back up Docker exec it, Redis 5, Redis CLI monitor. So now we have the Redis monitor so we can watch this all in action as well. So let's go over here. I don't know if I already did this, I'm just going to do it again. So I've now written our transformers into memory. Now I'm going to go through and I'm going to basically run the read input. So lazy promise, we print our schema. Category index is now like a string indexer that we saw before. So literally this is same exact as what we've done before, but now we're just throwing it all into a single pipeline function. So category indexer, string to indexer. Indexer has a transformer, so it can be serialized using the same stuff that we looked at above. Rating indexer is taking the string indexer again. It also has a transformer, so it can be serialized. So once we fit, great. We've done that just like we've done before. And this whole entire process can now get rolled into our pipeline. So index, category, index, rating, fit category, fit rating, same exact thing we saw before. And fitting in this case is literally an estimator that just takes the distinct values of a category, distinct values of a rating, and then basically throws it into a deterministic order. So that if we add more, then we're going to have the same ordinal values of the underlying data. Our encoder is our one-hot encoder, so we looked at that as well during the feature engineering section in part 3. So our one-hot encoder is now taking our category index, our rating index, and then it's also expecting the rating class, which we haven't defined yet, which is kind of interesting because we're basically setting up a future stage of execution, and we're basically expecting that the encoder is going to occur after the rating classification transformer has run, as well as the kid-safe transformer. And then lastly, as we've done before, we create our vector. So as we know, machines enjoy vectors. Machines can enjoy data. Our features is now basically, it's a vectorized matrix of individual values across category, across rating, and then our rating classifier. So we call that features. So basically, this is our pipeline phases. So when we create our transformer pipeline, we're doing it the same as we saw before. We just have a lot more kind of going on now. So it's kind of the complete series of transformations from reading in initially from Redis to the transformations that are ready now for our machine learning model. So transformation pipeline, new pipeline, set stages. We're going to use the fitting on the rating index, fitting on the category index. We're now using new, which is going to create a single instance of the rating classification transformer. Because we marked this with the default params writer, and we've actually set the UID, this will allow us to basically say, well, we can now serialize this pipeline using this explicit instance of the rating classification transformer. Same thing with our kid-safe transformer. Same exact process, we're calling new on it. So we're creating an instance that we're going to throw into this pipeline. Then we're going to be using our encoder, which is the one-hot encoder, followed by our vector assembler. Everything we just saw in a beautiful little pipeline. So when we call fit on the pipeline, all we're doing is basically fitting the initial data over here from content with categories, which is just basically a data frame with 3 different values. And then at the point where we fitted our pipeline, we can now save it. So we didn't look at saving before because we didn't really have to, because we're just taking a look at the basics. But when moving on to bringing something kind of closer to production, or being able to say even share your thoughts with somebody else, you can share it with notebooks, but notebooks can also mutate. I got some water over there. Given that notebooks can mutate, they're really good for experimentation. But as we're going to see moving on into part 5, at a certain point, you're going to really want to formalize your whole entire process so that nothing can mutate for a specific release. And this is actually a really good way of getting towards the ability to have a versioned release. So our pipeline at this point has now been stored off. So we can actually read from disk what our actual pipeline was, and then Spark will recreate exactly what we had, including the serialized individual functions that we added above. So that everything can be reproduced and it becomes completely deterministic for a version of a pipeline. So we see over there, fitted pipeline has a write method. So the fitted pipeline acts a lot like a traditional data frame. Because the underlying functionality in Spark is following kind of the same paradigms across the board, it feels natural. So fitted pipeline write, given that we are not going to be worried about things changing in the notebook, unless you decide you want to change it, we're calling overwrite, and we're saving a specific pipeline. In the case where you wanted to store different versions of this pipeline, because you've changed some settings, you've changed something else in that initial pipeline, all you could do is basically say, okay, well, it's learn pipeline, and now we're gonna have a way of versioning this. So maybe it's like, V1, you can go to V2, etc. It doesn't really matter. And then this could be stored someplace like S3, HDFS, you name it. Put on a floppy disk and mail it to somebody. I don't know. But in that case, you now have the ability to serialize your whole pipeline. So that actually ends up getting saved off. So /learn, as we've looked at like before, is the alias to the data directory in the Docker the Docker directory within this whole entire training. So this just allows you to basically say, well, we can now store this pipeline. We can use it later, or we can actually see what the pipeline was if we want to basically bring it into, say, Java, Scala, wherever else. It just gives us the ability to get back to it after we close down this Docker instance. All right, so transform. Take our fitted pipeline, and we're transforming our category with contents. So we know that was actually creating an action because we actually saw data being read out of Redis because we're using the Redis monitor. And then at the end of this, all we're doing is basically creating or replacing our temp view again for logistic prep. What this does is allow us to actually take a look easily at the underlying data, which is now stored in the kind of post-pipeline transformation. All right, so now we're going to look at the end result of the transformation that we made using our pipeline. So if we go down and we take a look at the end result of that logistic prep, we're going to scroll down and basically take a look. So we have our show ID, we have our category, and we have our rating. That was what we brought in from Redis. That was the initial data set. Across the transformation steps, we brought in our rating index, the category index, a rating class, and then the actual label. So kid safe or not safe for kids. If we think about kind of the underlying data, then part of the stuff is the way that I've taken a look at the data in the past. So TVPG might be kid safe, might not be kid safe. So if you want to go change any of these values to affect the end results, you could change that in the rating classifier for what you basically put into the underlying kid safe data. So if you wanted to add, say, TVPG, then all we have to do is basically go through and take a look at what the actual rating index was for, say, TVPG, go change that. So that's pretty much what you need to do. And you can go back, I think this is in Notebook 3. If you go through the output of all the underlying paragraphs, where we're actually inspecting the underlying indices when doing like the string to index, you can take a look at the values that are actually present there. And then from there, you can do whatever else you want to. And this is, again, only for the ratings. All right, so going back over here. So going through the first row, we have TVPG, rating index, etc. We also see the output of like the vectors that we've added. So we have our category vector, we've got our rating vector, then we have the rating class vector itself. And we were doing that during the one-hot encoding step. From there, we're actually now assembling everything that we know about our features into this underlying features data set. So this is basically what's readable by machines. And on the other side, we have what's readable by humans. So it's kind of taking a look at the polarization of, what you do when you're using, say, exploratory data analysis versus the end result of feature engineering. So this data set is also easier to kind of fit into memory as well as a bunch of kind of bloated string values. You can go through a bunch more stuff here. Take a look at TVMA versus like TVG. Take a look at exactly what you want. TVG is kid safe. Take a look at the ratings where the label is 1. Take a look at science and nature TVG. That feels friendly enough for the most part. There's a little bit of kind of inherent bias with, again, as I said before. You can change any of these values and take a look at the way that it actually affects the model as well. All right, so let's just dive into logistic regression. So we know so far that we've created our transformers, we've created our transformation pipeline, we've imported our data from Redis, we've actually set up everything to basically create our features for this logistic regression model. Now all we have to do is actually create the model. So we have our classification logistic regression. So we brought in the first of our supervised learning models. A logistic regression model, all it's trying to do is basically create a partition between things that are not kid safe and things that are kid safe. And it will do this by trying to optimize its predictions on each individual pass through the actual data. So it's going to iterate over our data 10 times, up to 10 times, I should say, because sometimes we'll see that things aren't actually going to get any better. It's using the label that we created by using our kid safe transformer. And from there, it's using something called ElasticNet. So ElasticNet, not going too deep into this, is basically a way of optimizing two different ways of penalizing the underlying fitting of the model. So if we think about every single pass, the first pass over our data, we're going to have basically a 0 or 1 value for our labels. But we also, given that their underlying features are going to be a little bit different for each row of data, the first pass might not be super smart. So we're going to have to adjust. How do we penalize what we thought was actually a true positive and ended up being a false positive? What was a true negative or a false negative? So we're going to have to basically adjust some weights. The way that's done, it's using two different techniques called L1 and L2 penalties. So L1 penalty is a lasso, and it's a lasso penalty or lasso regularization. The other is ridge regularization. So there's lasso and ridge regression. So when we say set elastic net parameter, all we're doing is basically balancing. Are we penalizing more off of lasso, or are we penalizing more off of ridge regression? So right now I'm saying 0.8. So if you think about 0 being lasso and then 1 being ridge regression, I'm now optimizing more towards a ridge regression, which is going to basically be like a wandering path. So that in the case of our data, we're going to be fitting between our 0 and our 1 across the slope. So think about like a right triangle. And then all we're doing is trying to create the correct path over the data so that we are optimizing for true positives. So is this actually kid safe or not kid safe? And everything else is just the way that we're handling those iterations. So you can adjust the regularization parameter. You could change the elastic net parameters. You could also change like the tolerance as well. You can leave all these values as defaults. So the tolerance and everything else, some of these are exposed just to show you what the underlying defaults are. Change anything to whatever else you want to. Get rid of it. It's completely fine. Also in our case, given that we're saying fit to intercept, we're also just trying to fit between a 0 and a 1. If you think about a line being the shortest path between a 0 and a 1, then given that slope, we're creating an intercept. So the intercept itself is really good for this problem. There's other problems where it's not going to be as good for them. So if you get rid of the fit intercept, you'll see that things are going to change just a little bit. But it's up to you to play around with this, to research and look a little bit more into it. Maybe even not even use logistic regression, because you find later that linear regression works a little bit better. But both of these actually work really well for this use case. So moving on, we have to basically fit our model. So how do we do that? Well, we do that by taking the data that's been labeled, which is our whole entire data set up to this point, and we're basically just partitioning that into an 80-20 split. So we're going to be randomly seeding that. So where we see this random seed, we're creating a random seed so that every time we run the same splitting on the array, we're going to always be doing a random split exactly the same way. So it's not necessarily random after the first pass, because we can always expect the same deterministic outcome. So you don't want to randomly train your model or test your model off of a random split every single time, because it's not going to basically tell you if things are getting better or it's getting worse. So if you're always using that same kind of test data to test the actual performance of your the predictive model, then this is one way of doing that. We'll see there's other ways of doing that as well. But in this case, it's an easier way of actually splitting your data, and we're hoping for the best. So it's kind of a naive first pass. All right, so then we move on. So LR fit training data. So it's our 80% fit of that training data. I'm not going to go too much into the objective history or ROC, but if you think about all that we're trying to do is basically fit a line so that we're partitioning between a 0 and a 1 value. That is what this data is showing us, is how the model is actually thinking during each individual pass. And then also how is it basically balancing between true positives, false positives, true negatives, and false negatives. So you can take a look at the F measure as well if you'd like. All right, so that's the basics. You can take a look at the actual coefficients. So if we take a look over here and we say, okay, well, what are the coefficients of the features? What is the intercept value that's been created after fitting? And then we can also see over here in this objective history. So we can take a look to see these underlying numbers. We'll see that they don't change too much. So as we're testing different parameters, we're going from basically 3.1 to 3.08 to 3.05, 4, and things don't really get much better after that. So we'll see, like right now we had 10 iterations. So we have these 10 data points. Given that, what is that? There's 1, 2, 3, 4, 5. So around like the 6th iteration, things don't really change much. And really on like the 2nd iteration, it doesn't really matter. We're going to be very close to having almost a perfect success rate. You could literally change the max iterations to 3. This data set's not super complicated. So modeling for a precise kind of accuracy in that prediction isn't super complicated. But all this data is here to basically tell you how did the model run, and what exactly has it done, and how has it actually optimized itself. So you can look at the output for all of that as well. And all right, so moving on. So we talk about transformation. So after fitting, like we've done before, we fit and then we transform our data. So transforming the data, as we know, is basically just adding a new column. So we have our test data. We're dropping our label because we're basically, not basically, it's a dumb word to say, it's not basic, but our test data had a label because it was part of the same data set that we used for training. Given that we're trying to predict the label, we can drop it because it doesn't matter for us for our actual transformation. So test drop label just removes that underlying column from our data frame. So linear model transform creates our predicted data. Predicted, then we're just going to dump this into another SQL view called logistic test. So we go through and we run. So just click run. We're going to go through and run the logistic regression model. So what could go wrong? This is our first pass through. So we're going to take a look now. All right. Blah, blah, blah. Hold on one sec. I don't know why I just barfed. All right. So going back over up to the top again. So I'm going to go run this again. So it seems like it broke the first time. So it's running, it's running, it's running, it's running, it's running. Great. Now it's completed. So let's go take a look at the first pass through over the logistic regression modeling process. So let's actually see what our accuracy is. Like how close are we to being able to predict something as being true positive or false positive. So we take a look. So we have false positive, true positive rate over here. At the end, things look decent, right? We have the ability to basically, maybe things work. So what we're going to see in a second is why tuning is actually important. So let's take a look first and say, okay, well, let's select everything from our logistic regression test. So limit 1,000. Take a look through and we'll see, okay, predictions are 0. Great. We have these horror movies in here. That's lovely. PG-13. But then we also have kids TV. So let's just take a look to see how well we will be able to predict our kids TV. And so kids TV is a 0 prediction, but it should actually show up as being kid safe. So what's going on? So let's take a first pass back over what we were doing before. So how do we potentially recover from this issue? So before I was saying that when we created our logistic regression model, we're using the ridge regression. So ridge regression is giving us the ability to basically kind of fit along like a wandering path. We're also fitting to an intercept. Lasso is basically squeezing things down into basically kind of a better different kind of partitioning over a different penalty. So right now, given that we are doing kind of an 80-20 split against more towards ridge regression versus the lasso, let's now change our value to 5. So let's do an even split. Let's see if this actually changes the output, because as we know, we want kids TV to show up as being kid safe. Not everything basically showing up as not kid safe because our model is busted. So run through the same problem again. We'll see that the objective history is basically changing a little bit more. Penalties and everything else are basically the F measure looks about the same as it did before. Let's see. So the original theory is that we're fitting across intercept. So run this again. Instead of just doing the limit 1,000, let's take a look at where prediction equals 1. So we'll see, oops, we broke it again. So changing the lasso or the ridge regression parameters in our ElasticNet is not going to actually affect the outcome. And so if you think about what it is that we're actually doing, trying to fit along an intercept is probably not correct. So initial idea failed. Initial idea of basically 0 to 1 failed because things are actually a little bit different. So let's take a look now at removing our intercept. So the reason for being able to test across a bunch of different parameters while we're tuning our model is so that we can actually adjust to changes. So we were basically thrown a curveball, and it basically broke our ability to predict something as kid safe or not kid safe. It's interestingly enough, our unsupervised model seemed to work better at this point. So let's run this again, not fitting towards an intercept. Run. All right. So see again, our objective history has changed, but after the first few passes, things haven't changed as much. But what we'll see is now we actually have a little bit more variance in the false positive rate and the true positive rate. At the point where we get down to 100% false positive and true positive rate. Great. see how this actually changes as well. We also were able to fit, again, everything under the curve. So if we do prediction 1, still we've got nothing underneath our predictions. So we're going to move back up here again. Now we're going to change the elastic nut params one more time. Running over the data. Looks like we've looks like we're crashing Spark. All right, let's go back one more time. Let's run this. Hopefully everything works. Running more of a lasso. All right, great. So now we have a lot more going on for each of our passes. It looks like we're doing a little bit more. So now let's go through and see if our predictions have been updated. Do we have anything? Oh, yay. There we go. We'll see that after a few passes, the initial idea of fitting to an intercept didn't work. Using only ridge regression as a penalty was basically making it so that we couldn't actually predict something as being kid safe or not kid safe. So now doing a split where we're basically more of a lasso penalty versus a ridge regression penalty is actually better for us in the long run. So again, tuning is something that is interesting if you know exactly what you're doing. And it's not just interesting, it's critical. So this was kind of the first example of, let's throw a curveball. Let's see it actually recover from that curveball. And now let's move on. So hopefully this has been interesting so far. Let's move on. Let's talk more about our real talk. So one of the things I thought was kind of interesting at this point is that, by kind of doing, using kind of out of the box models, not needing to know much about how the models work, you're able to actually tune fairly good accuracy with just a few kind of iterations over the underlying fitting of that model. But the real talk is basically that, we have the ability to get to a perfect score. And a lot of times in the real world, you're not going to necessarily get to a perfect score. If you're getting, above 85% accuracy on your model, it's pretty great. In certain cases, you don't want pretty great. You want to, have a little bit better, accuracy in general. So at a certain point, you have to make a trade-off. So say you're a doctor and you're trying to predict cancer by taking a look at MRIs, or I don't know, I'm not a doctor, but if you're able to feed images into a system and you're basically classifying things as being cancer or not cancer, if the probability of it being cancer is fairly high, and it's, say it's above 75%, most likely you're going to want to go in and you're going to investigate that in the real world through some kind of surgery and taking like a biopsy. In other cases, like say it's fraud, sure. We think it's pretty close to an 80% fraudulent score. Let's go do something. And these are the trade-offs you're going to have to make when trying to answer a question with machine learning. So at what point are you satisfied with the current predictions that your model is giving? And also, what does it cost for you to get any better predictions? So if you think about, people's time, CPU, GPU costs, a lot of that stuff adds up over time. And for a lot of stuff, having, in our case, it's like above 90% accuracy. But if we're getting, maybe 80% accuracy across the board, it's pretty successful. You can always get better and better and better and better. You can throw more complicated models at things, but a lot of times logistic regression, which is a fairly simple modeling technique, will actually fit the bill for a lot of things. Plus, it's also really fast to be able to do this online. And we'll take a look at, basically, we're looking at linear regression during our streaming portion of this whole training. But logistic regression performs well online without needing a lot of computational power. All right, that's my real talk. So we'll move on from here. So we took a look at logistic regression. We're able to do really good for the most part. We're able to now predict when things are kid safe or not kid safe, and we actually have data. We were able to get past the curveball that we wrote into the system by selecting the wrong parameters. But what we're going to look at next is the ability for Spark to actually select the right parameters for us as well. So we're using this regression evaluator. So what we did manually was basically evaluate the regression process for the classification through logistic regression. Now we're looking at linear regression. Grab some water. All right, so this is now linear regression, not logistic regression. We're going to basically use a lot of the same parameters that we used before. So we're saying we're going to iterate 10 times, and we're going to, again, hope for the best. But now we're going to use a params grid builder. So what this params grid builder does is it basically says, well, we have the ElasticNet param, which we looked at before. So we have 0 to 5 to 1. So from lasso to split between lasso and ridge regression to ridge regression. We also have the regularization parameter, which is basically affecting each iteration over the data. It's affecting the ability for us to penalize and basically fit the underlying model. From there as well, we're saying fit to intercept. So linear regression has a line. And so in this case, fitting to the intercept is going to make a little bit more sense than what we're doing with logistic, where although we wanted to fit to a line of basically a 0 to a 1, we found out that the fitting to the intercept for our data didn't actually work as expected. So here we're going to basically throw these parameters into the mix. And now, given that this is a grid for fit intercept with the regularization parameters, as well as the ElasticNet params, what's going to actually happen is that Spark will actually test different variations of these different parameters through different fitting passes on the underlying model. So this is, if you think about like the world of like AutoML, a lot of AutoML is basically just doing this for you. So it's allowing the system to basically pass multiple times over your data to be able to create the best of the best from the available data, create the best model. All right, so moving on. So we create our params grid builder. This is coming from ML tuning. It's the tuning process. And then we're also bringing in this train validation split. So train validation split, what is this doing? So we know that we have an estimator. We talked about transformers and estimators before. Our estimators are now our linear regression. So linear regression model has been only built at this point to basically take 10 iterations. From there, we're feeding everything else with this elastic, the params grid builder. Like I was going to call it elastic grid. So over here, we're saying, okay, well, we're setting now the evaluator, and we're setting the estimator params map to be the params grid. And then we're using a regression evaluator to ensure that we're basically getting the best tuning out of this regression model. Linear regression is a regression, great. Our train ratio is now 80. It's going to be 80%. So before we basically were manually splitting our data. In this case, it's going to automatically train our data, split our train data more effectively through cross-validation. And then it's going to do it for us behind the scenes. We don't have to be smart about it. But if you think about, say, kid safe, not kid safe, then if we have a label that's 1, and then we also have a label that's 0, if we were to do a random split, there's a chance that most of our content might not actually have a label of 1 in it. So then we're training towards something that doesn't have enough content to basically feed the fitting process. So it's not going to be as accurate. But if you're able to basically split so that you have a better split between what's labeled with a 1 and a 0 in both the training and the test, then you can actually accurately say that your model is performing well. And this is just a way of actually having Spark do almost all the work for you. You just have to basically set it up. So think about this as a tuning pipeline, as before we had a transformation data pipeline. So now if you move this, if you mix all this stuff together, we now have the train validation split pipeline feeding in from our other transformation pipeline for the data. And now this is basically just pipelines and pipelines. And at the end of the day, the output of this pipeline is a trained model that performs extremely well. So we're going to run this, and we're going to talk a little bit more about it. So hopefully my Spark doesn't crash again. Run. All right, sweet. So it finished, no crashes. This is perfect. All right. So over here, we'll see that we fitted our model. So we ran the validation split. We're also choosing best parameters. Great, so that's been fit. All of our output, you can go through all of that. It's basically just telling you what are the parameters that we ran. So before we had to basically say, well, are we going to fit the intercept or are we not going to fit the intercept? Because we actually gave that Boolean value, it's going to basically test with fitting, without fitting, with fitting, without fitting, across our different parameters as it goes. So in this case, you think about the elastic net params as a 0.5. There's also one in there as well, as this kind of continues on as but this is basically just getting truncated for the output. So what are the different passes? Instead of us manually having to figure out what's going on, like we were doing above, now we're just having Spark do this all for us. So we have the model and it's been fitted. Great. We have a pipeline that's been fitted. If we want to save a model, this is really no different than how we actually fitted our pipeline. So if you take a look over here, we have our logistic regression or linear regression model. We're allowing an overwrite again because we're not changing what we're doing now that it's all been fit. So model, write, overwrite, save, and this is just basically going to our local data directory, and it's LRM, so linear regression model. I would actually ask, if you want, take a look at the Docker directory at this point in time, and take a look at what's actually in the LRM directory. I can give you a hint. It's going to tell you everything that it's done, and it's going to also have a best model. So if you think about the way that we were kind of tuning with this AutoML, you're basically testing a bunch of different hyperparameters, and you're tuning and training multiple times, and a model that basically performs the best will not just be marked as best model. So if you have a long offline job that's running for a while, it might be up like in a Docker container somewhere else, could be across an entire gigantic Spark cluster. You're going to probably walk away from that. You're going to come back later, and you're going to hope that the job completed. At that point, you'll have a best model. And then from there, you can basically say, okay, well, for this version of the model, for this version of the pipeline, let's now save this all off. So this is basically the end result of that. So we've saved the linear regression model, and we've serialized all the phases of execution. We've also kept track of what the actual parameters were for the hyperparameters that led to the model being as accurate as it was. Given that a model is just predicting an outcome, we've now created a system that can predict really well if something is kid safe or not kid safe. We glance over this whole object transformers right now. This is basically just kind of showing how you would basically put this, or not basically again, but how you put this into your code. So you might want to create an object, which is a static class. In this case, there's only one transformer object. Transformer then has a pipeline location, a model location, and then if you want to go defrost your pipeline or defrost your model, all you're doing is basically deserializing that back into an object. So we're basically loading a pipeline model, or we're loading the train validation split model. And then from there, we have our transforms. So if we want to say, okay, well, I'm going to now take data, and I want to transform that data through the pipeline. Now that I've actually stored off and saved these, both the pipeline and the model, at this point, all I'm doing is saying, well, we read the data from Redis. We're going to call transform, and then we're going to call predict. And that's going to be able to basically do exactly what we've done in this entire notebook so far. All right, so that's pretty much it. So I'm going to just play this over here. And now we're basically doing exactly what we've seen in the past. So transformers predict, test is dropping the label, and we're creating this predict linear. Predict linear is now a temporary SQL view. And predict is basically coming in from our defrosted trained best model. So it's linear regression, and now we're taking a look at the the success or the failure of what that was. So if we take a look over here, we've got TVG, 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 etc. And we basically we're just taking a look at ordering this by prediction. So we take a look, we're over 100% accuracy on a lot of stuff, dropping down a bit. In this case over here, just kind of keep on going through all of this. So are we closer to 1 or not? So we take a look at, say show ID, rating, and prediction, predict linear. And we're going to basically say where rating is in TVMA, R, unrated. Then we can go through, we can do the same thing, press OK. So see over here, So the closer to 1 that we are, the better. And in this case, we're basically, we're very far away from actually being kind of a true positive. So we go over now to, say we go to G. Let's take a look at G. See -4, by the way. So it's not 8. So over here, we're very close to 1 versus being so far away from 1 that we'll never ever be close to it. So you think about these predictions and say, how well is this model actually, how well is this working? That's very polarized. So from G, which is super close to 1, that was supposed to actually play. All right, to R, which is now super, super, super close to like almost absolute 0. This is really able to partition extremely well. That's pretty much all you really need to do is be able to take a problem and be able to predict it. That's all we've done. Is we've taken the Netflix data, and this is pretty much the end result of what I'm calling kind of the batch process. So from Notebook 1 to Notebook 2 to Notebook 3 to Notebook 4, we're now at the end result where we've created an entire transformation pipeline. We've trained our logistic regression and linear regression model. We've seen how well the linear regression model performs. We've seen how to basically use AutoML techniques to optimize and tune our hyperparameters. And now we've also seen how well things actually work for the system actually knowing if something is kid safe or not kid safe. So I'd say like right now we're excelling as very A+ students at our job at learning how to basically be machine learning engineers or data scientists for a fairly simple problem. But also at the same time, you can apply what we've learned across the board to not so trivial problems. And you can use a lot of the techniques that you've learned so far to be able to really think rationally about the decisions that you're making and also the trade-offs. So is 80% or 85% accuracy great? Do you need better accuracy? Do you need worse accuracy? Like what do you do? For like a really complicated data set, you're not going to necessarily get to 90 or 100% accuracy, or like what we've seen over here, where it's basically very much kid safe, not kid safe, and just weigh the pros and cons of what it's worth to get another percentage point towards your accuracy. So with that said, I have I have my conclusion notes, and you can read through that in the notebook as well. Without basically further ado, we're going to end this part of the training, and we're going to follow up with one more special training that's not linked directly here, which is basically how do we actually apply this to streaming using Redis streams. So all we're doing at the point where we want to basically run this online is we take everything that we've learned offline. We've taken our trained and fitted model. We've taken our serialized pipeline. And all we're doing is saying that we're freezing this at this point so that data that's coming in stream can now feed through the same pipeline, be transformed through the model, and then we can basically just predict a 0 or 1 value. So was it kid safe or not kid safe? We're going to take a look at that next. But thank you for bearing with me through the first 4 of these long sessions. And hopefully the end result of all of this is that you have a really good context for moving forward with Redis within your Spark operations. So thanks a lot.